So warm-up question says, sit as still as possible and then turn and look at your neighbor. How fast are they moving right now? Anybody want to volunteer an answer for how fast is your neighbor moving? Yes, sir.
0 miles an hour.
Sure, 0 miles per hour. It's probably the answer most of you said. Okay, probably. Did anybody say anything other than 0? No? That's okay. That's what I was expecting you to say. Okay, now I will say this. 0 is correct, so long as you define your frame of reference as relative to you. Okay, and that's what we're going to talk about today, is how we can define all of our motion is always defined relative to some point. And we've talked about this before when we first started talking about motion, but today we're going to talk about what happens whenever the point that we are comparing our motion to is also moving. Okay, in your lab yesterday, for example, you guys picked a point on the floor and you measured all of your distances from that point. That was your reference point. Okay, and so you defined your frame of reference and you said this is our point we're going to measure from. We're assuming this point to be stationary. Okay, going back to your warm-up, again, you can assume that the person next to you is stationary if you're comparing their motion to the floor or the walls or you. But you can also come up with some very different answers depending on your frame of reference. Okay, so you could say that you're not moving compared to your neighbor, and if you said 0 meters per second or 0 miles per hour, then that's exactly what you did. However, if you want to think outside the box a little bit and pick a different frame of reference, you could say that your neighbor is moving 750 miles per hour east relative to the Earth's center, because that is the rate at which the Earth rotates as it is turning on its axis. So you could have said that. Now, probably didn't, but you could have. You could have also said that you're moving at 66,000 miles per hour because that's how fast the Earth is moving around the sun as it moves in its orbit for that, whole year. That's how fast it moves. You could have also said that you're moving at 483,000 miles per hour because our entire solar system, which includes our sun and our planet and you and your neighbor, is moving at 483,000 miles per hour relative to the center of the Milky Way galaxy. So again, depends on how you define your frame of reference. And lastly, and there are more you could have put, but this is where I stopped, our entire galaxy is moving toward Andromeda at 1.3 million miles per hour. So you could have said that you're moving 1.3 million miles per hour relative to Andromeda. Okay, it all depends on your frame of reference. And so that's what we're going to talk about today, is how we define our motion. And we'll start with what a frame of reference is. We have talked about this already, but we're going to get into it again. But before I do that, I'm first going to let you watch a little clip that illustrates the same points that I was just making. It's a short little TED Ed cartoon that's kind of interesting, and I would definitely recommend that you pay attention to it.
How fast are you moving right now? That seems like an easy question. The first tempting answer is, I'm not moving. Upon further reflection, you realize that maybe the Earth's motion counts. So a second tempting answer is 19 miles per second around the sun. But then you recall learning that the sun moves around the center of the Milky Way galaxy. And the Milky Way moves within the local group of galaxies. And the local group moves within the Virgo cluster. And the Virgo cluster moves within... How fast are you moving is not an easy question. When mission control tells astronauts how fast they're going, there is always an assumed standard of rest. At the start of the voyage, speeds are given relative to the launch pad. But later, when the launch pad is just one more arbitrary place down there on Earth's spinning surface, speeds are given relative to the idealized, non-spinning, pinpoint center of Earth. On their way to the moon, Apollo astronauts had a hard time answering the question, how fast are you moving? Speed away from Earth was one thing, and speed toward the moon was quite another. That's because the Earth and the moon move relative to one another. Of course, speed is a relative quantity. When Captain Kirk asks Lieutenant Sulu if the Starship Enterprise has reached a speed of warp 7, Sulu should reply, relative to what, Captain? Such a sassy reply may get subordinate Starfleet officers in trouble, but it is the only good answer to the question, how fast are you moving? This is basic relativity talking. Not fancy Einsteinian relativity, but good old-fashioned and still correct Galilean relativity. Galileo seems to have been the first person to realize that there is no such thing as an absolute speed. Speeds are relative. This means that speeds only have meaning when they are referred to a reference frame. Presumably, that reference frame is itself at rest. But then we have to ask again, at rest relative to what? Because even the concept of rest has lost any hint of absolute meaning. Speed is relative and rest is relative. Earth's speed is 19 miles per second relative to the sun. The Enterprise's speed is warp 7 relative to the center of the Milky Way galaxy. Your speed is 0 relative to your easy chair. But depending on where you sit, it is hundreds of miles per hour relative to Earth's center. When we furrow a brow and ask, but how fast is Earth really moving? We imagine spaceship Earth plowing through the ocean of space as it orbits the sun. But space is not an ocean. It has no substance as water does. Space is not a thing. Space is nothing. Space is no thing. You can move between 2 points in space, say between Earth and Mars, but you can't move through space. There's nothing to move through. It's like trying to say how much a hole weighs. A hole weighs exactly nothing, because a hole is nothing. It's a void, and so is space. To move relative to nothing is meaningless. The concepts of speed and of rest have only relative meaning. They are absolutely meaningless. They mean something only with respect to arbitrarily chosen, artificial frames of reference. If someday you are buckled into your spaceship and you see from the side window, say, a space station whiz by at constant speed, there is no way to know which of you is really moving. Neither of you is really moving because there is no deep reality about constant speed. Constant speed in a straight line has only relative meaning, a kind of relative reality. Does this mean that all motion is relative? No. Some motions have only relative meaning, but some motions have absolute meaning, are absolutely real. For example, constant speed is relative, but change in speed is absolute. Calling something absolute in science means that arbitrary standards are not used in its measurement. It is unambiguously measurable. When your spaceship fires its engines, your change in speed is beyond doubt. You feel it in your stomach, and your ship's sensors can measure it. Outside your window, the passing space station may seem to be changing speed, but the beings inside the station will not feel it, and no sensors can measure it. You are really changing speed, and they really are not. There's something absolutely real about changes in speed. The same goes for rotation. If your spaceship is spinning, you can feel it, and your ship's sensors can measure it. The space station outside may seem to be going around you, but it is you who feels queasy, not the folks in the space station. You are really spinning, and they really are not. There's something absolutely real about rotation. So some motions are relative, and some are not. There is no deep reality about constant speed, but changes in speed are deeply real, and so are rotations. We have to be thoughtful in our analysis of everyday experience in order to identify what is deeply real. Since we can be fooled by perceptions as basic as speed, maybe every perception deserves careful scrutiny. This is what inspired Einstein to his incredible insights about the speed of light and forward time travel. Knowing how to identify what is deeply real is tough and important work. If a police officer ever pulls you over for speeding and asks, "Do you know how fast you were going?" an insightful, though perhaps unwise, reply would be, relative to what? And then, as you sit in the back seat of the police car and feel it accelerate toward jail, you can add, "But some things are absolute."
I would not recommend saying that to a police officer. All right. Although it is true, it is relative, and that's the point. Okay, so I said we're going to start by going back over frame of reference because we have talked about this already whenever we first started talking about motion, but we define our frame of reference by choosing a reference point and describing objects' change in position compared to this point. Again, that's what you did in yesterday's lab. You picked a point on the floor, you said this is going to be 0, we're going to measure everything from here, and you let the car go. Okay, and so you defined your reference point and thus your frame of reference by assuming that point to be stationary. Even though it's on Earth and even though Earth is moving, we can assume that point to be stationary and then look at how objects move compared to that point. Okay, or another example, when you left home and drove to school today, you could say that you were moving with respect to your house. In this example, your initial position, your home, would be your reference point. You could say, you know, I drove 3 miles east to get to school, or whatever. Again, you would be describing your position and your motion with respect to that frame of reference. Oftentimes you are the reference point and you describe things with respect to your position because you're describing them from your point of view. For example, he was running away from me, or she ran right past me. Okay, and so you have defined that frame of reference as yourself. But it doesn't have to be you. Okay, you can define it as anything you want, or pick a point on the floor, like in the lab yesterday. But we can only describe motion with respect to a reference point. So if you look at this example, it's kind of similar to the warm-up question. When compared to the buildings along the road, the girl in the passenger seat is moving. Just like when compared to the sun, you're moving. Okay. However, when you compare her to the driver, she's not moving anymore. When you compare your motion to your neighbor's, you guys both seem stationary. So again, it depends on how you're defining that reference point as to whether or not you would say that you're moving, or whether she's moving. Okay, so how relative velocity is how we describe motion when our reference point is moving. And again, technically, all of these things are in motion. So it's somewhat arbitrary to say this point is stationary when we know that it's not, because we know the Earth is moving. Okay, relative velocity is the mathematical comparison of two or more objects' velocity. So some examples to think about: how fast do the trees appear to move when you are sitting in a moving car? When you drive home today, or maybe you're riding home with a friend or your mom, and you look out the window, the trees look like they are moving. You know they're not, but they appear to be moving to you. And so they do have a relative velocity relative to your frame of reference, to your perspective. Or you could look at, you know, your mom or your friend, whoever's driving, and relative to them, you're not going to appear to be moving. It's the same example as in the warm-up. Okay, so again, when we talk about relative velocity, there are 3 basic examples that you're going to see. And I'm going to go over the 3 of them. There's really only 3, so I would copy these down if I were you. Because, again, when we're talking about relative velocity, we're talking about how the velocity of an object appears from some other frame of reference, which in this case we're going to talk about a lot of frames of reference that are also moving. Okay, so when you are moving, objects that are approaching you from the opposite direction will appear faster than their actual ground speed. When you're driving down the road and somebody is coming the opposite direction toward you, they're going to look like they're moving faster. Okay, especially if you're on a 2-lane road and there's just that center line keeping you guys separated, they're going to seem like they zoom past you. They appear faster than they're actually moving because they're moving and you're moving, and so you're moving relative to one another, and it makes their speed appear faster. On the other hand, if you're driving down 99 and you're trying to be a law-abiding citizen, so you're going 70 miles per hour, which nobody does that, and then the person next to you drives past you going 87 miles per hour, okay, you know they're going fast because you know you're moving, but from your perspective, if you assume that you're stationary, then they only look like they're going 17 miles per hour because that's how much faster they're going than you are. So objects that are passing you while going the same direction appear slower than their actual ground speed. If you're going 60 miles an hour and somebody else is going 61, okay, then that person only looks like they're moving 1 mile per hour faster than you, which is annoying whenever there's 2 people next to each other doing that and you're trying to pass. Okay, I know you'll know what I'm talking about. Okay, but objects passing you in the same direction appear slower than their actual ground speed. So those are the first 2 possible cases. Things moving opposite direction toward each other, things moving the same direction where you're moving, where something's passing you. Of course, the other would be you're moving the same direction, you're passing them. Okay, that's the third case, is if you pass another object because you're moving the same direction, or maybe that object is stationary and you pass it like the trees out the window. Okay, that object will appear to move backwards. So again, if you are driving down the road and you look out the window, the trees look like they're moving backwards from your perspective. If you imagine yourself in this red car and you look out the window to your right, that gray car looks like it's moving backwards relative to your position. Okay, and slower than it's actually going as well. But again, those are the three possible cases. So we're going to go over some examples, and you can copy down each of them so that you have some of these to look back at because you will have similar types of problems today. Okay, so here is an equation that allows you to calculate the relative velocity of two objects as long as both of those objects are moving, their motion is described with respect to the ground. Okay, if you have a different situation where you have a moving object and another moving object inside of that object or on top of that object, it's different. Okay, so just a heads up, because you will have some examples like that. You cannot use this equation for those examples. Okay, so this one says calculate relative velocity, and the equation says the velocity or relative velocity, V sub rel for relative, equals the velocity of the object minus the velocity of the observer. You being the observer, whatever perspective you're trying to take. So if you look at this, it says you're driving east at 50 miles per hour when a wrong way car comes at you 40 miles per hour to the west. How fast does the wrong way driver appear to move from your frame of reference? And here is a animation of somebody doing just that, driving the wrong way on the road. Okay, and so if you think about this, this is a scenario where the two cars are moving opposite directions. You're going east, they're going west. And we just talked about what that's going to be like. If you're moving opposite direction, they're going to appear faster than they're actually going. So although they're only moving 40, from your perspective, they will appear to be moving faster than that. And so let's figure out if we can use this equation to determine how much faster, or maybe you can just reason your way through it. I'm sure you can. Okay, but first things first, velocity is a vector, and when we're trying to determine our relative velocity, we need to take into account the direction. So if I'm going east and they're going west, I'm going to call east positive and I'm going to call west negative. So when I plug my numbers into this equation, I'm going positive 50, they're going negative 40, and so that's what I have. Relative velocity equals negative 40, because they're going west, minus positive 50. I didn't write the positive sign, I just wrote minus 50. Okay, but those are the values that I substituted in. And so negative 40 minus 50 is negative 90 miles per hour. And again, that negative sign is a direction. Specifically, it means west in this example. And so that wrong way driver would appear to be moving 90 miles per hour to the west, because again, they look faster to you than they're actually going. You're going 50, they're going 40, it looks like they're going 90. Again, you could do that probably logically, but you can also do it with this equation. All right, so that's the first example. If you're moving toward one another, let's look at another one. You're driving on a track at 125 miles per hour and a black car passes you at 140 miles per hour. How fast is that car moving from your perspective? So now we're in race cars. Okay, and again, you're in the red one and this car is passing you. Now you're both going the same direction. It doesn't say what it is, so let's just call it positive because that's easier to work with. And we can plug into the same equation. I already know that if somebody passes me from my notes that we wrote down a couple slides ago, that they're going to appear slower than they're actually going. So even though they're going 140, they're not going to look like they're going 140 from my perspective. Okay, so if I plug it in, you're going to see that. Here's their 140 miles per hour. Here's my 125 miles per hour. We're both going the same way. So positive 140 minus positive 125. And we get a relative velocity of positive 15 miles per hour. Again, that positive sign just means they're going in the same direction that you're already going. 15 miles per hour faster than you. That's how fast they're going to look, because they are driving 15 miles per hour faster than you. They're going to look like they're moving 15 miles per hour as they move away from you. So again, that is slower than they're actually going, so they appear slower. All right, last example was what if you pass someone else? So here's that. You're driving north in a red car at 50 miles per hour as you pass a blue car traveling north at 30 miles per hour. How fast does the blue car appear to move from your perspective? What is its relative velocity? Again, I already know that if I pass someone, they look like they're moving slower than me. or slower, but also backwards. Okay, so if I look at my equation, the objects, in this case, both of us are going north, so we're going to have the same sign for both. I'm going to call it positive. The object is the blue car going 30. I'm going 50. 30 minus 50 is negative 20. Again, that negative sign is a direction. If north is positive, then south would be negative in this case, and that means that they appear to be moving 20 miles per hour south, or from my perspective, 20 miles per hour backwards, because I'm passing them. Okay, are there any questions about these examples?
Well, when it's still, they would still be moving forward.
They are still moving forward, but if you look out your window when you pass someone, from your perspective, they look like they're moving backwards. This doesn't mean they're actually driving in reverse. Okay, or even that they're actually traveling at that speed. Their speedometer says 30. Your speedometer says 50. But from your perspective, they look like they're moving 20 miles per hour backwards. Does that make sense?
Mm-hmm.
Okay. Any other questions? All right. Let's try some of these examples. You're going to see this picture again. It's in your assignment today. Okay, so this would be a good thing to pay attention to. If you are riding in the boat, what is the apparent velocity of each from your frame of reference? This boat is moving 12 meters per second west. Okay, and it wants to know how fast the bird appears from the boat's perspective. Well, the boat's moving 12. The bird is moving 17 in the same direction. So, they're going the same way. The bird's faster than you. How much faster? 5 miles, or meters per second in this case, but yes, 5 meters per second faster, okay, but it's still going to look like it's going west. So its velocity will appear to be 5 meters per second west. Again, you don't have to go to the equation, you can just do it logically. Okay, the person right here standing on the shore that's not moving, this would be like when you're driving down the road and you pass the trees. Okay, if you're moving 12 meters per second as you go down the river or drive down the road, how fast does the person look like they're moving? They look like they're moving 12 meters per second backwards from your perspective.
Are you talking about the bird?
I'm talking about the person now. Okay, just like the trees. When you drive 60 miles per hour down the road and you look out the window, the trees look like they're moving 60 miles per hour backwards from your perspective. Okay, and the car, this is the example where they're moving toward each other. Okay, the boat's moving 12, the car's moving 32. If they're moving toward each other, is the car going to look like it's moving faster or slower than it actually is going? Faster. Okay, so instead of 32, now it's going to look like it's moving 44 meters per second because the boat's 12 and the car's 32. It's still going to look like it's going east. Okay, the only time that it's going to look like it's moving backwards is if you are passing it. Okay, that's going to change the direction. So again, you're going to see questions like this. You're also going to see questions like this. What if we add in a current to the river? So now the boat's speedometer says 12 meters per second, but the river is going 3 meters per second east. Is that going to make the boat move faster or slower? Slower, because it's fighting against the current. Okay, so the boat would then be only actually moving relative to the shore, would only be moving 9 meters per second instead of 12. Again, that changes how you analyze the rest of these scenarios. Okay, I'm not going to go through all of these. Y'all are going to do it anyway on your own because you have this assignment, 103.4, Relative Velocity Problem Set in Schoology. You're going to go into the same Google Sheet. You're going to get your link for today, and you are going to work on this for the rest of the class period. If you have questions as you're working, let me know, but otherwise I'm going to let you guys get to it. You're welcome to consult with a neighbor, but remember you do have different questions than they do, so please make sure that you're not copying theirs. It's not that. Okay, it's 103, guys. If you open 103, there were links to different Google Forms, so make sure you open up the right assignment, 103 problem set. Open it up, and you're looking for the link for 103.4 Relative Velocity Problem Set. If you don't finish it in class, it is due by 11:59 p.m. tonight.